Hi everyone, welcome to this video. Here we'll talk about the main objects of linear algebra, which are matrices. Matrices and vectors are really what we're going to be talking about until the end of the course. Let's consider three vectors, u, v, and w, as follows. We have u with 1, -1, 0, v with 0, 1, -1, and w with 0, 0, 1. If we consider a general linear combination of these three vectors, it could look like this. It could be x1u plus x2v plus x3w. Let me write that with the vectors inside. So that is x1 multiplying the first vector, 1, -1, 0, plus x2 multiplying the second vector, 0, 1, -1, plus x3 multiplying the third vector, 0, 0, 1. What these vectors produce, if you carry out the multiplication, you're going to get x1 from the first vector, nothing from the second, and nothing from the third because they're being multiplied by 0. Then the second component will be -x1 plus x2, and x3 is multiplied by 0. And the third component will be -x2 from the second vector plus x3 from the third vector. We got this answer, right? The linear combination, any linear combination of three vectors will produce another vector. Now, what is interesting is that we can rewrite this equation using a matrix in the following way. I'll use the three columns, u, v, and w, to be the columns of a matrix, looking like this. I'm going to write 1, -1, 0, then 0, 1, -1, then 0, 0, 1. I'm going to multiply that by a vector consisting of the numbers x1, x2, x3 to get the answer, which is x1, -x1 plus x2, -x2 plus x3. We denote the matrix here by A. Let's label this vector a vector X, and the answer, let's call it a B. So what we have is an equation, a matrix equation, AX equals B. A refers to that array of 9 numbers, which are, you could think of coefficients, and then the vector x consists of the three unknowns x1, x2, and x3. We don't know why they're unknowns just yet, but usually when we use x, we kind of mean we're going to be looking for those coefficients. So let's translate this problem into an example where we have a particular b, let's say. If we say take x to equal 1, 4, 9, then b, if you just replace the numbers, would be 1, then -1 plus 4, and -4 plus 9, which is equal to 1, 3, 5. So in some sense, what we did was we applied the matrix A onto this vector 1, 4, 9, and it gave us the vector 1, 3, 5. That means that we can think of A as transforming the vector x, or let me use numbers, but it's the vector x equal to 1, 4, 9 into the vector b equal to 1, 3, 5. So what this does is it allows us to look at matrices not simply as objects that summarize some coefficients for us, but actually as transformations and as actions. And this will be a central theme in the course. We'll think of A as doing something to x. It in fact multiplies x to give b. Now, in what way do we carry out that multiplication? What is that a times x? If you look here, a times x is defined by how we know to multiply or by really taking a linear combination, right? This linear combination here is something we know how to do. We multiply the first column by x1, we multiply the second column by x2, we multiply the third column by x3 and add them up to get the answer b. That is what's referred to as column multiplication of a matrix. Now, I know some of you have seen matrices before, and usually in most textbooks, matrices are really kind of matrix multiplication is defined through its rows. Let me get back to that. So remember, AX, I'll write the matrix again, is 1, 0, 0 if I write the rows, negative 1, 1, 0, 0, negative 1, 1, times the vector x1, x2, x3. Now, if I want to carry out this multiplication by the rows, which is in fact possible, the definition really here is row 1 dot product the vector x, row 2 dot product the vector x, row 3 dot product the vector x. We know how to take the dot product. Let's carry that out and let's see what we get. So the first one, row 1 dot product x, is really this vector, the first row written as a column because our vectors are always columns, dot product with x1, x2, x3. Remember, the dot product is product component-wise. The two vectors multiply each other component-wise, and then those different products are added. So we have 1 times x1 plus 0 times x2 plus 0 times x3, and that adds up to x1. Now, if we do row 2 times x, we are using negative 1, 1, 0, that is the second row of the matrix, times the vector x1, x2, x3. We get negative 1 times x1 plus 1 times x2 plus 0 times x3, and we get negative x1 plus x2. And finally, row 3 times x, which will be 0, negative 1, 1, dot product x1, x2, x3, and we get 0 times x1 minus 1 times x2 plus 1 times x3, and we get negative x2 plus x3. So you see, no matter how you multiply the matrix, whether it's by the rows or by the columns, you are going to get the same answer. Now, row multiplication is, and using the dot product, is convenient if we know the x's. If we are working with numbers and we just want to compute the answer and see what the product was. But conceptually, it is much better to work with the columns because we look at the answer of ax equal b over here. We see that b is in fact a linear combination of the columns of A. Let me write that. B is a linear combination of the columns of A. And this will be the key idea that we all have to get through our heads. This is going to be repeated almost every class until the end of the course. And remember, when you have a linear combination, you need to know exactly how to combine the columns of A. Well, that information is stored in X. So where X tells us, or where the vector X tells us how to combine the columns of A. Now remember, I mentioned we're using x's here as unknowns. That is because sometimes we're going to be given the vector b and we're going, well, not sometimes, but rather more often than not, we're going to be given a vector b and we're going to ask the main question. Is there a combination of the columns of A that produces a b? And that is the same question and saying, can we find an x so that ax equals b? Okay, we'll continue about this more in the next video.